Imagine gazing into the night sky and wondering what lies beyond the farthest stars we can see. For centuries, the edge of the universe has sparked both intrigue and confusion, challenging our understanding of existence itself. With recent advancements, scientists are daring to peel back the layers of this cosmic enigma, embarking on an exploration that intertwines theoretical concepts with observable data. We delve into persistent mysteries of our universe, from groundbreaking research and observational challenges to innovative ideas that push the boundaries of known physics. The quest to understand what lies beyond our observable limits is closer than ever. The universe's boundaries. The concept of the universe's boundaries is a fascinating topic that challenges our understanding of space and time. Currently, scientists describe the universe as expanding, much like a balloon being inflated. This expansion means that galaxies are moving away from each other, and the farther away a galaxy is, the faster it appears to be receding. However, when we think about the edge of the universe, things become more complicated. There is no solid boundary in the traditional sense. Instead, the universe may be infinite or finite but unbounded. Imagine the surface of a sphere. A traveler moving in any direction could continually explore its surface without ever encountering a physical edge. Similarly, our universe can be thought of as having no definitive outer limit, where space itself curves back on itself. As we look deeper into the cosmos with newer telescopes, we can see light from stars and galaxies that were formed billions of years ago, painting a picture of the universe in its infancy. This observable universe, which is the part we can detect, is constantly expanding, leading to the question of what exists beyond what we can observe. Some theories suggest that there are regions of space that could remain forever out of reach, shrouded beyond the limits of our observational capabilities due to the finite speed of light and the ongoing expansion of the universe. Further complicating the understanding of boundaries is the notion of the cosmic horizon, which defines the limit of our observable universe. Beyond this horizon, events cannot be observed because their light has not had enough time to reach us since the beginning of time. Understanding these limits not only broadens our view of the cosmos, but also raises profound questions about the nature of reality itself. Current scientific understanding presents the universe as a vast, dynamic expanse with no clear boundaries, where our visible surroundings are shaped by complex factors like expansion, cosmic structure, and the laws of physics that govern everything we see. The edge of the universe is a fascinating concept that scientists approach from several angles. First, it's important to clarify that in the vastness of space, there isn't a physical boundary like the edge of a table. Instead, the universe is expanding, and this expansion can be envisioned as everything moving away from each other, much like dots on an inflating balloon. Scientists often define the observable universe, the portion we can see and study, by considering the distance light has traveled since the beginning of time, following what is known as the Big Bang. Light from the furthest reaches of this universe has taken billions of years to reach us. Therefore, the observable universe is essentially a sphere centered on Earth, encompassing everything whose light we can currently detect. When considering where the universe might end, we delve into the realm of theoretical physics. Some theories suggest that the universe could be infinite, stretching on forever without an edge. Others propose that the universe might curve back on itself, creating a sort of cosmic loop. In this case, if you travel far enough in one direction, you could potentially return to your starting point. Ultimately, the edge of the universe is entwined with the limits of our knowledge. As our observational technologies improve and our understanding of cosmic phenomena evolves, we may gain new insights that could redefine how we perceive the universe's boundaries. For now, the edge serves as a reminder of both our curiosity and the vast mysteries still waiting to be unraveled in the cosmos. Our journey to understand the universe. Our journey to understand the universe's size has evolved dramatically over centuries. In ancient times, people viewed the cosmos as a small, intimate space revolving around Earth, which they considered the center of everything. The stars were thought to be fixed points in the sky, and the universe was seen as a vast yet accessible expanse that could be fathomed by the human mind. This perception began to shift during the Renaissance, when astronomers like Copernicus proposed that the Earth was not central, but instead orbited the Sun. This heliocentric model expanded the perceived scale of the universe. As telescopes were developed, figures like Galileo and Kepler revealed a wealth of detail. Planets with moons, distant stars, and even the Milky Way itself, which was recognized as just one of many galaxies. In the early 20th century, our understanding took another leap forward with Edwin Hubble's observations, demonstrating that galaxies are moving away from us, indicating that the universe is expanding. This finding transformed our view of the cosmos, suggesting not just a vast number of galaxies, but also a universe that is continuously growing larger over time. Further advancements in technology, such as space telescopes, have uncovered millions of galaxies, each containing billions of stars. This explosion of knowledge has led to the realization that the universe is enormously larger than previously imagined, possibly infinite. Today, scientists ponder not just the dimensions of space, but also the nature of dark energy and dark matter, which play crucial roles in the universe's expansion. Our perception continues to evolve, now faced with concepts like the multiverse and the idea that there may be realms beyond what we can currently observe. Each discovery pushes the boundaries of our understanding, inviting us to consider not just the vastness around us, but our place within this immense cosmic arena. This ongoing exploration not only expands our comprehension of the universe's size, but also deepens our awe and curiosity about what lies beyond the horizons we have yet to explore. Tools and technologies. Exploring the universe's boundaries requires an array of advanced tools and technologies designed to capture the vastness of space and the phenomena within it. One of the most fundamental instruments is a telescope, which comes in various types. Optical telescopes, for example, gather light from stars and planets, allowing us to see objects many light years away. Meanwhile, radio telescopes detect signals emitted from celestial bodies, providing insights into the universe's behavior, even in darkness or through cosmic dust. Space missions rely heavily on spacecraft equipped with sophisticated instruments. Space observatories, like the Hubble Space Telescope, orbit above Earth's atmosphere to achieve clearer images without atmospheric distortion. These observatories can observe a wide spectrum of light, from ultraviolet to infrared, revealing details about distant galaxies, starbursts, and exoplanets. Another crucial technology is spectroscopy, which breaks down light from celestial objects into its component colors. This technique allows scientists to analyze the composition, temperature, speed, and even the movement of distant stars and galaxies. By studying how light shifts towards a red or blue end of the spectrum, researchers can infer whether an object is moving away from or toward us, shedding light on the universe's expansion. Additionally, space probes and rovers, such as those that have explored Mars and the outer planets, send back invaluable data about planetary atmospheres, surface compositions, and potential habitability. These robotic explorers function in extreme conditions, gathering information that ground-based missions could never achieve. Gravitational wave observatories represent a more recent technological advancement, designed to detect ripples in space-time caused by massive cosmic events, such as merging black holes or neutron stars. This innovative tool opens a new window into the universe, allowing scientists to observe phenomena that light alone cannot reveal. Together, these tools and technologies form a multifaceted approach to unraveling the mysteries of the universe's edges. They provide critical insights that help us understand the very nature of reality, how galaxies form, and ultimately, the origins of the universe itself. When we look into the night sky, we see light from distant galaxies, and this light has traveled vast distances to reach us. The further away a galaxy is, the older the light we see, allowing us to glimpse back in time. However, there exists a limit to how far we can see, known as the observable universe. Beyond this boundary lies regions from which light has not yet had enough time to reach us since the Big Bang. The Big Bang Theory also leads us to consider what could lie beyond our observable universe. While we cannot see these areas, understanding that our universe is expanding suggests there is much more out there that remains hidden from our view. This idea invites questions about the structure, composition, and fate of the universe as a whole. Are there other bubbles of space, each with its own distinct properties? The quest to answer these questions has opened up exciting avenues in astrophysics, continuing to shape our understanding of the cosmos and the limits of our knowledge. In grappling with the implications of the Big Bang, we also confront profound mysteries, such as dark matter and dark energy, two phenomena that compose a large portion of the universe, yet elude direct observation. Each discovery builds on our understanding of the universe's evolution and pushes the boundaries of what we know, as scientists seek to unravel the intricacies of what lies beyond the confines of our immediate perception. To comprehend the observable universe, we first need to recognize that it consists of a vast assembly of components that together create the cosmos we see. At its most fundamental level, the universe is populated by galaxies. These immense collections of stars, gas, dust, and dark matter can contain millions to trillions of stars. Within these galaxies, stars are born, live out their life cycles, and eventually die, often in spectacular events like supernovae, enriching the cosmos with heavy elements. In addition to stars, many galaxies host planetary systems. These systems can include a variety of celestial bodies, such as planets, moons, asteroids, and comets. Our own solar system is one of countless examples, with the Sun at its center and numerous planets revolving around it. These planets may harbor conditions suitable for life, making them a significant area of interest for scientists. Another critical aspect of the observable universe is dark matter. Despite being invisible and detectable only through its gravitational effects, it plays a crucial role in shaping galaxies and the large-scale structure of the universe. Dark matter accounts for a significant portion of the total mass, influencing how galaxies are formed and held together. Moreover, the universe is permeated by cosmic microwave background radiation, a remnant of the Big Bang. This faint glow uniformly fills the universe and serves as a critical clue for understanding its early moments and expansion. Lastly, we cannot forget about the vast empty spaces between galaxies, known as cosmic voids. These areas might seem vacant, but they are essential to the universe's architecture, providing insights into the overall distribution of matter and energy. Together, galaxies, stars, planets, dark matter, cosmic radiation, and vast voids create a complex, interwoven fabric of the observable universe, providing a dynamic landscape where cosmic phenomena unfold. This intricate interplay between all its components shapes our understanding of the universe's origins, evolution, and ultimate fate. Dark matter and dark energy are two of the universe's most enigmatic components, each playing a crucial role in its structure and behavior. To grasp their interaction with the edges of the universe, it's important to first understand what they are. Dark matter accounts for a significant portion of the universe's total mass, acting as an invisible glue that holds galaxies together. It's neither dark nor matter in the conventional sense. Rather, it's a substance that does not emit, absorb, or reflect light, making it impossible to detect with standard observational tools. However, its presence is inferred through its gravitational effects on visible matter. On the other hand, dark energy is thought to fill the universe and is responsible for its accelerated expansion. While dark matter pulls objects together, dark energy pushes them apart, countering the force of gravity on the cosmic scale. This dual nature of attraction and repulsion highlights the tension in the universe. Dark matter tries to clump matter together, while dark energy works to spread it out. Now, when we consider the boundaries of the universe, we encounter a dynamic interplay. Dark matter influences the distribution of galaxies and clusters of galaxies, shaping the large-scale structure of the universe. It helps form the cosmic web, an intricate structure consisting of filaments and voids that delineate the universe's architecture. As dark matter aggregates, it creates gravitational wells that capture nearby matter, forming galaxies and galactic clusters. In contrast, dark energy plays a more pivotal role in the universe's overall fate, especially as it nears its boundaries. While the universe is expanding, dark energy accelerates this expansion, potentially leading to scenarios where galaxies drift further apart over cosmic timescales, making the visible universe increasingly sparse. As galaxies move away from each other due to this expansion, the scales of separation reach a point where distant galaxies may become invisible due to the finite speed of light. Effectively, dark energy defines the outer limits of our observable universe, leading to the possibility that regions currently visible may eventually slip beyond our observational reach. Together, dark matter and dark energy create a complex evolutionary landscape for the universe. Dark matter holds structures together and facilitates the formation of cosmic architectures, while dark energy shapes its long-term destiny by driving accelerated expansion. This interplay not only influences the universe's current structure, but also its future development, hinting at profound implications for understanding existence beyond what we can currently observe. The cosmic horizon. The cosmic horizon represents the boundary of the observable universe. Imagine standing on a vast ocean with no land in sight. The horizon is where the ocean appears to meet the sky, marking the limit of what you can see. In the context of the universe, the cosmic horizon signifies the farthest distance from which light has had time to reach us since the beginning of the cosmos. Because the universe is constantly expanding, this horizon sets the limit on what we can observe or gather information from. This boundary is significant for several reasons. First, it delineates the extent of our knowledge. Beyond the cosmic horizon lies regions of space that are forever unreachable for us, as light from those areas has not had enough time to travel to Earth since the universe began. This introduces interesting questions about what exists beyond our observational reach. Moreover, the cosmic horizon has implications for our understanding of cosmic events. It helps scientists map the early universe, providing insights into phenomena like cosmic inflation, which describes an incredibly rapid expansion shortly after the Big Bang. By studying the cosmic microwave background radiation, the afterglow of that early universe, we gain valuable information about the conditions that shaped everything we see today. Ultimately, the cosmic horizon represents both the vastness of space and the boundaries of human knowledge, inviting exploration and curiosity about the universe that lies beyond what we can currently observe. The exploration of the universe's edge beckons theories that extend far beyond what we have imagined, entwining the fate of our cosmos with the potential of infinite others. Cosmic microwave background radiation, or CMB, is a fundamental remnant from the early universe. Imagine the cosmos as a hot soup filled with particles and energy existing just after the Big Bang. About 380,000 years after that monumental event, the universe was so hot and dense that light couldn't travel freely. It was constantly scattered by charged particles. As the universe expanded, it cooled down enough for electrons and protons to combine and create neutral hydrogen atoms. This allowed light to escape, creating a blanket of radiation that fills the entire universe today. This radiation is no longer the intense heat it once was, but has stretched and cooled into microwave wavelengths due to the expansion of the universe. At that time, the universe was so hot and dense that light couldn't travel freely. It was constantly scattered by charged particles. As the universe expanded, it cooled down enough for electrons and protons to combine and create neutral hydrogen atoms. This allowed light to escape, creating a blanket of radiation that fills the entire universe today. This radiation is no longer the intense heat it once was, but has stretched and cooled into microwave wavelengths due to the expansion of the universe. When we observe the CMB, we're essentially looking back in time, capturing a snapshot of the universe's infancy. This light provides crucial insight into the universe's age, composition, and structure. The relevance of CMB to universal boundaries lies in its uniformity and the tiny fluctuations present within it. These fluctuations represent the earliest seeds of all cosmic structures, galaxies, stars, and clusters. By studying these variations, scientists can infer the density and distribution of matter throughout the universe, helping them establish models of how it has evolved over billions of years. Furthermore, the CMB acts as a boundary of sorts. It defines the observable universe, marking the limit beyond which we cannot gather information in a meaningful way. Anything beyond this cosmic horizon simply lies beyond our reach. Light from those regions of space has not had enough time to reach us since the birth of the universe. Thus, the cosmic microwave background not only serves as a relic from a pivotal moment in cosmic history, but also sets a physical boundary to our observations and understandings of the universe. Wormholes present fascinating challenges to our understanding of the universe and its boundaries. Traditionally, we picture the universe as expanding outward, with galaxies moving away from one another over vast expanses of space and time. This view holds that the edges of the universe are not physically defined. They represent regions beyond which we cannot see or travel due to the limitations of light speed. Now, imagine introducing a shortcut to this cosmic landscape. A wormhole would act like a bridge, connecting 2 points in space-time that are far apart. This means that, theoretically, one could traverse the universe much more quickly through a wormhole than by following the traditional route through the vast emptiness between stars and galaxies. This possibility raises questions. If such shortcuts exist, what does it mean for the nature of distance and the ultimate edge of the universe? Conventional scientific theories posit that the universe is expanding uniformly. Yet, if wormholes were proven to exist, this could imply regions of space that are interconnected in ways we do not yet comprehend. The edges of the universe, thus, might not be as absolute as we thought. They could be penetrated or even bypassed. Current understanding suggests that nothing can travel faster than the speed of light, preserving the integrity of space-time. However, wormholes challenge this paradigm, suggesting a complex structure to the fabric of the universe that might permit instantaneous travel. The implications stretch beyond mere travel. They touch on critical concepts, such as causality and the very nature of reality. For all the imaginative solutions wormholes offer, they also bring to light anomalies that conventional theories struggle to integrate. Thus, the existence of wormholes could force scientists to reconsider and expand upon our current models, reshaping what we understand about the universe's layout and edges. The concept of parallel universes opens up fascinating possibilities that can profoundly shape our understanding of the limits of the universe. Imagine a vast multiverse, where every decision or event creates a branching path leading to infinite variations of reality. Each of these realities exists independently, yet is influenced by the same foundational rules of physics that govern our own universe. When we consider parallel universes, we start to challenge the limitations we typically attribute to our understanding of existence. For instance, if multiple realities coexist, what does that mean for concepts like time, space, and causality? In our universe, we are constrained by certain physical laws, like the speed of light as a maximum speed limit, or the singular nature of time flowing in one direction. But in a multiverse scenario, it's possible that different universes could operate under alternate physical laws or dimensions, stretching the very framework of what we deem possible. This idea encourages us to question the uniqueness of our own universe. If there are realities where fundamental forces behave differently or where time might loop back on itself, it begs the question of whether our current scientific laws are entirely universal or merely applicable to our specific universe. Each discovery we make in our universe could prompt a reevaluation of those laws if we consider that other versions of reality might have discovered different truths. Ultimately, the existence of parallel universes suggests that the limits we perceive may only be the edges of our understanding. Expanding our perspective to include these alternate realities allows scientists to explore new theories, challenge long-standing assumptions, and approach the mysteries of cosmology and physics with greater imagination. Thus, Parallel universes and extra dimensions don't just challenge our understanding of the universe. They invite us to broaden our horizon of what is possible beyond the confines of our observable reality. Extra dimensions play a pivotal role in contemporary theories regarding the universe's structure. While we perceive the universe through three spatial dimensions, length, width, and height, some advanced scientific models suggest there could be additional dimensions beyond our immediate grasp. These dimensions can be thought of as hidden or curled up, existing at scales far smaller than we can observe with current technology. At the heart of these theories, like string theory, is the idea that the fundamental particles we observe are not simply point-like dots, but rather tiny, vibrating strings. The vibrations of these strings are influenced by the geometry of higher dimensions. Each configuration of these extra dimensions affects the physical properties of particles, such as their mass and charge, ultimately contributing to the richness of the universe we experience. The significance of these extra dimensions extends beyond mere speculation. They could help explain some of the universe's most profound mysteries. For instance, these theories might provide insights into the force of gravity as we know it, which remains weaker compared to other fundamental forces. By theorizing extra dimensions, scientists propose that gravity could be spilling into these additional dimensions, making it appear weaker in our three-dimensional experience. Furthermore, the shape of the universe might be influenced by these dimensions, potentially allowing for a more complex, multidimensional structure than the flat or curved spaces we can visualize. Understanding these dimensions helps physicists grapple with questions about the universe's early moments, black holes, and the integration of quantum mechanics with general relativity. Extra dimensions expand the framework within which we comprehend the universe. They offer a broader canvas for exploring fundamental forces, guiding researchers toward a deeper understanding of the very fabric of reality itself. To understand how they help us glean information about the edge of the universe, imagine these particles as messengers from the far reaches of space. They originate from various sources, including supernova explosions and active galactic nuclei, extremely energetic centers of distant galaxies. When cosmic rays travel through the universe, they interact with magnetic fields and other particles. This journey can change their direction and energy, acting like a cosmic GPS system. By studying how these particles arrive at Earth, scientists can infer details about their origin and the environments they traveled through. The characteristics of cosmic rays, such as their energy distribution and composition, reveal crucial information about the conditions in space, including the presence of magnetic fields and the density of intergalactic matter. Specifically, cosmic rays can indicate the presence of regions where energetic events occur, suggesting the boundaries of our universe and potentially the structures that define it, such as galaxy clusters. Moreover, cosmic rays can help us indirectly probe the nature of dark matter, an elusive substance that makes up a large portion of the universe. By examining the patterns in cosmic ray arrivals, researchers gain insights into how dark matter interacts with particles, thus offering a glimpse into the universe's composition and the forces at its edges. Through ongoing research, cosmic rays serve as a valuable tool for expanding our understanding of our cosmic environment, unveiling the mysteries that exist at the very limits of our universe. Cosmic background noise poses significant challenges to scientists trying to study the universe. To visualize this, think of cosmic background noise as a clutter of static and whispers that blend into the rich symphony of the cosmos. This noise primarily comes from remnants of the Big Bang, known as the cosmic microwave background radiation, which radiates uniformly throughout space. While this ancient radiation is essential for understanding the early universe, it can be overwhelming. One of the main difficulties lies in separating the signals scientists want to detect from this pervasive noise. Imagine trying to listen to a faint conversation while a loud crowd is cheering nearby. In the vastness of space, measurements can be distorted by many factors, including this background noise, which hampers the detection of weaker signals from distant galaxies or unseen dark matter. Moreover, the instruments that scientists use to observe the universe, such as telescopes, can also introduce their own noise. Just like an old radio may produce additional crackling sounds, telescopes can generate unwanted signals from their electronic systems or from ground-level sources, which mix with the cosmic noise, further clouding the data being collected. To mitigate these issues, researchers employ advanced techniques, such as signal processing methods, to filter out the noise and extract meaningful information. This requires not only complex algorithms, but also a deep understanding of both the desired signals and the noise they must contend with. Ultimately, navigating through this cosmic cacophony is crucial for unlocking the mysteries of the universe and gaining insight into its formation and evolution. Gravitational waves are ripples in the fabric of space-time, produced by some of the most violent and energetic processes in the universe, such as colliding black holes or neutron stars. Imagine dropping a stone in a pond and watching the waves ripple outward. In a similar way, these gravitational waves spread out through space, carrying crucial information about their origins. When these waves traverse the universe, they can pass through matter almost undisturbed, providing a unique glimpse into events that might otherwise be hidden from view. This ability to travel through obstacles like stars and galaxies allows scientists to study phenomena that are difficult to observe through traditional means, such as light. By detecting these waves, researchers can infer the properties of the massive objects that created them, such as their masses, spins, and distances. Understanding the patterns and characteristics of these waves helps astronomers piece together the behavior of the universe itself. For example, by analyzing the waves resulting from a black hole merger, scientists can learn about the formation and evolution of black holes, challenging existing theories about how they develop. Furthermore, gravitational waves provide insights into the expansion of the universe by revealing details about its rate and history. This new avenue of cosmic investigation opens doors to studying aspects of the universe that we may not yet fully understand, such as the inner workings of neutron stars or even the elusive nature of dark matter. Gravitational waves serve as a cosmic messenger, telling us about the structure of the universe in ways that light cannot, enriching our understanding of the cosmos and answering fundamental questions about its nature. Gamma-ray bursts are among the most powerful explosions in the universe, often regarded as cosmic beacons that guide scientists into the depths of space exploration. These bursts emit an immense amount of energy across a wide spectrum, with gamma rays at the forefront. Imagine them as flashes of light that occur when massive stars undergo cataclysmic collapses, leading to supernovae, or when two dense neutron stars collide, creating a surge of energy that outshines entire galaxies for brief moments. The significance of gamma-ray bursts lies in their incredible luminosity. They can be observed from vast distances, making them visible even billions of light years away. This allows astronomers to peer deeper into the universe's history than with many other astronomical phenomena. As these bursts occur in regions that may be far removed from our own galaxy, they act like lighthouses, illuminating the distant cosmos and providing insights about the conditions of the early universe. Furthermore, the study of gamma-ray bursts has immense implications for understanding cosmic structures and processes. By analyzing the light emitted from these events, scientists can learn about the composition and behavior of the interstellar medium where the bursts occur. This information unveils details about star formation, the life cycle of stars, and the evolution of galaxies. In a broader context, gamma-ray bursts challenge our understanding of fundamental physics as they push the limits of what we know about gravity, matter, and energy. They inspire technological advancements as researchers develop tools and methods to detect and interpret the signals coming from these distant explosions. As instruments become more sophisticated, our exploration boundaries expand, revealing the universe's mysteries and enriching our comprehension of cosmic phenomena. The dance of light from gamma-ray bursts isn't just a spectacle. It actively shapes our quest for knowledge about the universe. What we can see is just a small portion of the universe's total mass. As a result, theories now expand beyond ordinary matter, incorporating strange and elusive components that shape cosmic structures. Similarly, dark energy, which seems to be responsible for the accelerated expansion of the universe, suggests that we may not fully grasp the nature of space itself. This driving force challenges the notion that gravity, which pulls objects together, is the only significant player. Instead, our comprehension of the universe's fabric must adjust to account for these powerful, unseen influences. Gravitational waves, detected through their minute ripples in space-time, have opened new avenues for understanding cosmic events, such as black hole mergers and neutron-star collisions. These discoveries remind us that the universe is dynamic and filled with interactions that can reshape existing theories. Each of these enigmatic phenomena influences theoretical boundaries, urging scientists to delve deeper, whether by proposing new models or reevaluating existing ones. This ongoing investigation reflects humanity's insatiable curiosity and highlights a reality where the universe remains an ever-expanding puzzle. It's through these mysteries that our understanding stretches across time and space, continually redefining what we think we know about the cosmos. Astronomical anomalies, those unexpected or unexplained phenomena in the cosmos, serve as crucial puzzle pieces that can upend established theories about the universe. When astronomers observe something that doesn't fit the expected patterns, like stars behaving strangely or galaxies displaying an unusual distribution of mass, they are confronted with the limitations of their current understandings. These anomalies prompt scientists to dig deeper, forcing a reevaluation of existing concepts. Take dark matter, for instance. It was proposed to account for the mass discrepancies seen in galaxies. When scientists noted that these celestial bodies spun at such speeds that they should logically tear themselves apart, they introduced the idea of an unseen substance providing the necessary gravitational pull. Yet, the exact nature of dark matter remains elusive, with many anomalies hinting that perhaps the universe operates under different rules than we currently comprehend. Similarly, observations of rapid expansion in the universe led to the concept of dark energy, which represents another significant anomaly. The pressing question arises: why is the universe expanding faster now than it did in its earlier stages? This counters conventional ideas that gravity should slow that expansion over time. Such evidence reshapes our understanding, suggesting that there are invisible forces at play that we have yet to fully understand. Each anomaly acts as a catalyst for innovation, urging scientists to develop new theories or modify existing ones. As researchers confront these mysterious phenomena, they explore concepts like quantum physics, altered gravitational laws, or new dimensions of space. In this way, anomalies don't just challenge our understanding. They pave the way for breakthroughs, inspiring questions that broaden the horizons of cosmic knowledge and pushing the boundaries of science further into the unknown. Ultimately, they remind us that the universe is vast and full of surprises, often leading us to discover more than we ever thought possible. At the boundaries of our understanding, where the universe presents its most perplexing phenomena, scientists face the challenge of reconciling theoretical predictions with observed reality. When observations contradict established theories, such as those regarding the behavior of distant galaxies or cosmic events, scientists undertake an intricate process of investigation. First, they examine the data rigorously, ensuring that the observations are accurate, reliable, and free from interference. Advanced technologies and methods, including sophisticated telescopes and computer simulations, help to refine the information they gather. This meticulous scrutiny is essential. Sometimes, the contradiction arises from a simple error in measurement or data interpretation. When data integrity is confirmed, scientists revisit the theoretical framework that produced the conflicting predictions. They might consider whether adjustments or enhancements to the existing theory could resolve the dilemma. This iterative process often leads to modified or entirely new models that better account for the observed phenomena, illustrating the dynamic nature of scientific inquiry. In cases where contradictions persist, they may prompt a paradigm shift, leading scientists to develop novel theories that challenge our fundamental understanding of the universe. For instance, the discovery that the universe is expanding at an accelerating rate led to the introduction of dark energy as a new concept revolutionizing cosmological theories. Ultimately, scientists engage in dialogue, sharing findings and encouraging collaboration across the global research community. This collective effort fosters creativity and innovation, enabling researchers to explore alternative explanations and blend insights from various fields. In this way, contradictions between theory and observation at the universe's edge not only deepen our understanding, but also drive the pursuit of knowledge further into the cosmic unknown. Deep space phenomena act as portals to understanding the universe's complexities. Observations of distant galaxies reveal a vast tapestry woven with threads of cosmic events that date back to the universe's infancy. For instance, studying the light from these ancient galaxies provides insights into their formation and evolution, highlighting the intricate processes that have shaped them over billions of years. One of the most compelling mysteries illuminated by deep space observations is the existence of dark matter. While it cannot be seen directly, its presence is inferred through the gravitational effects it exerts on visible matter. This has led scientists to speculate about the nature of this unseen substance, which appears to make up a substantial portion of the universe, fundamentally altering our understanding of gravity and structure formation. Similarly, the discovery of cosmic microwave background radiation, a remnant from the early universe, has given researchers a glimpse into the conditions that existed just moments after the Big Bang. This faint glow provides critical data supporting the Big Bang theory, revealing that the universe began in a hot, dense state and expanded over time, cooling and evolving into the cosmos we see today. The phenomena of supernovae, the explosive deaths of massive stars, play a key role in revealing the distribution of elements throughout the universe. These events not only create and scatter heavy elements, but also serve as standard candles for measuring cosmic distances, allowing scientists to map the expansion of the universe and the mysterious acceleration that seems to drive it. Additionally, observations of gravitational waves from colliding black holes and neutron stars have opened a new chapter in understanding the universe. They confirm predictions of Einstein's theory of general relativity while presenting an entirely new way to gather information about cosmic events that were previously undetectable. Thus, the study of deep space phenomena continues to peel back the layers of the universe's mysteries. From the nature of dark matter and energy to the formation of cosmic structures, each observation adds pieces to an ever-expanding puzzle, fueling humanity's quest to comprehend our existence within this vast and largely unknown cosmos. Quasars, short for quasi-stellar objects, are among the brightest and most energetic entities in the universe. They serve as remarkable cosmic beacons, illuminating our understanding of extreme conditions and events in the universe. At their core, quasars are powered by supermassive black holes that reside at the centers of distant galaxies. As surrounding gas and dust swirl into these monstrous black holes, they are heated to incredible temperatures, producing vast amounts of energy that can outshine entire galaxies. One of the most profound contributions of quasars to our understanding is their role in probing the early universe. Many of the quasars we observe today emitted their light billions of years ago, which allows astronomers to glimpse how galaxies evolved shortly after the Big Bang. By studying the light from these distant quasars, we can uncover details about the composition of the universe at that time, including how matter was distributed and how the early galaxies and stars formed. Moreover, quasars are instrumental in exploring the fundamental laws of physics under extreme conditions. The immense gravitational and energetic forces that surround a quasar can lead to phenomena not easily observed elsewhere. For instance, they provide insight into the behavior of matter and radiation in environments where gravity is extraordinarily strong, which can test our understanding of general relativity and the limits of known physics. Quasars also offer valuable information about the expansion of the universe. By measuring their light across vast distances, scientists can calculate how quickly the universe is expanding and the rate at which it has changed over cosmic time. This can lead to conclusions about dark energy, a mysterious force that seems to be accelerating this expansion. By observing and studying quasars, we not only appreciate some of the most extreme environments in the universe, but also gather crucial clues about the universe's origins, evolution, and the fundamental forces that govern it. These fascinating objects illuminate paths to knowledge, pushing the boundaries of what we understand about space and time itself. Faint galaxy clusters, which are groups of galaxies held together by gravity, serve as valuable cosmic touchstones for understanding the universe's history and structure. These clusters are often located far from our own galaxy, making them challenging to observe. However, their faintness is not a drawback. Instead, it allows scientists to delve deeper into the mysteries of dark matter, dark energy, and the evolution of cosmic structures. When astronomers look at these distant clusters, they engage in a kind of cosmic archaeology. The light we see from them today actually left those clusters billions of years ago, providing a glimpse into the universe's past. By studying their composition and how they are distributed across the cosmos, scientists can gather data about the distribution of matter in the universe. This information helps paint a clearer picture of dark matter, which, while invisible, makes up a significant portion of the universe's mass. Moreover, the way light bends around these clusters reveals essential insights into their mass and gravitational influence through a phenomenon known as gravitational lensing. Imagine using a magnifying glass to focus light on a distant object. Gravitational lensing works similarly, allowing us to observe objects further away than we could ordinarily see. This distortion of light provides clues about the underlying mass and structure of the clusters and, by extension, the distribution of dark matter throughout the universe. Faint galaxy clusters also play a crucial role in understanding the expansion of the universe. The characteristics of these clusters can inform scientists about the influence of dark energy, a mysterious force thought to drive the universe's accelerating expansion. By analyzing the distances and interactions of various clusters, researchers can piece together how dark energy has shaped cosmic evolution over billions of years. While faint galaxy clusters may initially appear insignificant, they are, in reality, woven into the very fabric of cosmic investigation. They guide us toward understanding the strange and elusive elements that govern the universe, bridging gaps in our knowledge from the earliest epochs to the current expansion, and keeping the quest for cosmic understanding ever more profound. Fast radio bursts, often referred to as FRBs, are among the most captivating phenomena in astrophysics today. These brief yet intense flashes of radio waves originate from vast distances, potentially billions of light years away. Their sudden bursts can last just a few milliseconds, but they unleash more energy than the sun emits in nearly a century. What makes these cosmic signals particularly intriguing is their mysterious nature. Each burst appears to come from deep space, yet we have only detected a small fraction of them. Their origins remain largely unknown, leading scientists to propose a range of intriguing possibilities, from the collapse of massive stars to interactions involving neutron stars, or even the cryptic effects of magnetars, which are exceptionally magnetic neutron stars. The frequency and the way FRBs are scattered give researchers clues about the cosmic environment through which their signals travel. For instance, the dispersion of the radio waves as they move through space can highlight the presence of matter in the universe that we might not be able to see directly. This helps scientists construct a map of cosmic structures that influence how light travels across vast distances. Moreover, the ability to detect these bursts and pinpoint their locations opens up new avenues for understanding the evolution of the universe. By studying their patterns and frequencies, researchers hope to unlock secrets about the conditions in the early universe, the formation of galaxies, and the way cosmic matter interacts. The captivating mystery of FRBs invites scientists to explore deeper into the effervescent dance of celestial bodies, encouraging new discoveries and enhancing our understanding of the cosmos. Cosmic voids are vast regions of space that contain very few galaxies compared to the areas around them. These enormous expanses can be thought of as the empty parts of the universe, often spanning hundreds of millions of light years. Understanding these voids helps us grasp not only the large-scale structure of the universe, but also hints at the boundaries of our cosmic neighborhood. The existence of cosmic voids suggests a fundamental aspect of the universe's composition. As galaxies clump together under the influence of gravity, they form a web-like structure, with dense regions or filaments surrounding these voids. This arrangement indicates that space is not uniformly distributed. Rather, it shows a complex tapestry where matter is concentrated and where vast emptiness exists in between. When we discuss universal boundaries, we often touch upon the limits of our observable universe. Cosmic voids contribute to this conversation because their presence hints at how matter and energy distribute throughout the cosmos. While we can see only up to a certain point, the edge of the observable universe, voids might extend beyond that boundary into regions we cannot detect. These sparsely populated areas also raise intriguing questions about the universe's topology, the shape, and the structure of space itself. If we think of the universe as a three-dimensional balloon being inflated, cosmic voids might represent those patches of surface that have been less stretched out. They challenge our understanding of what lies beyond our visible realm, prompting questions about the universe's ultimate fate and whether it extends infinitely or is instead contained in some uncharted manner. Cosmic voids are not just empty space. They embody the variety and complexity of the universe. They illustrate how the idea of boundaries in the universe might be perceived, suggesting that while we know our observable universe has limits, the true nature of the cosmos could lead us to vastly different landscapes we have yet to explore. Cosmologists play a vital role in unraveling the mysteries surrounding the universe's edge, a concept that refers to the farthest regions we can observe and the limits of our understanding. They blend observational science with theoretical frameworks to explore the expansive cosmos. By employing advanced telescopes and instruments, cosmologists capture light from distant galaxies, allowing them to construct a detailed map of the universe. These observations reveal the composition and structure of the universe, including vast cosmic structures like galaxy clusters and the distribution of dark matter. Moreover, cosmologists utilize the principles of general relativity and the laws of physics to formulate models that explain how the universe has evolved since its inception. They analyze phenomena such as cosmic background radiation, a remnant from the birth of the universe, providing insights into its early conditions and subsequent expansion. By exploring how galaxies move and cluster, they can infer the universe's overall geometry and curvature. The quest for understanding the universe's edge also leads to investigating cosmic inflation, a rapid expansion that occurred just after the Big Bang. This theory posits that the universe grew exponentially in size, setting the stage for the structures we see today. Cosmologists work to validate or challenge this theory through meticulous analysis of the cosmic microwave background and high redshift objects, which are galaxies that existed when the universe was much younger. In addition, cosmologists delve into dark energy, a mysterious force believed to be driving the accelerated expansion of the universe. By measuring galaxy distributions and light from supernovae, they attempt to understand how this expansion impacts cosmic structures and what it means for the ultimate fate of the universe. Their ongoing research not only enhances our comprehension of the universe's edges, but also inspires new questions about what lies beyond our current observational limits. Through these contributions, cosmologists are piecing together a comprehensive narrative about the universe, bridging gaps in knowledge and certain mysteries that remain tantalizingly out of reach. Astrophysics and cosmology are two branches of astronomy that, while distinct, are deeply intertwined in the quest to understand the universe. Astrophysics delves into the physical properties and behavior of celestial bodies, studying everything from the life cycles of stars to the nature of black holes. In contrast, cosmology focuses on the universe as a whole, exploring its origins, evolution, structure, and ultimate fate. The intersection of these fields becomes particularly evident when examining the universe's boundaries. Astrophysics provides the tools to analyze specific phenomena that shape our cosmic landscape. For instance, The understanding of the life cycle of stars is crucial in cosmology when considering how elements are forged and distributed throughout the universe. These elements contribute to the formation of galaxies, planets, and eventually life itself. Conversely, cosmological theories offer a broader framework that astrophysics can explore in finer detail. The Big Bang Theory, a cornerstone of cosmology, posits that the universe has been expanding since its inception. Astrophysicists utilize this concept to investigate the redshift of distant galaxies, revealing how light from these galaxies shifts toward longer wavelengths as they move away, providing evidence of the universe's expansion. This helps delineate the boundaries of the observable versus unobservable universe, leading to questions about how much of the universe lies beyond what we can see and measure. Together, these fields collaborate on fundamental questions about dark matter and dark energy, which significantly influence the universe's expansion and structure. Astrophysical observations of gravitational waves and cosmic microwave background radiation feed cosmological models, refining our understanding of the universe's composition and evolution. While astrophysics gives us insight into the individual components of the cosmos, cosmology provides the overarching narrative, allowing humanity to probe the limits of our universe and ponder what lies beyond. This combined effort enriches our understanding, opening dialogue about the potential for multiple universes, the nature of space-time, and the ultimate fate awaiting all existence. The investigation of the universe's boundaries showcases the importance of approaching these questions from both astrophysical and cosmological perspectives. Technological advances in physics have a profound impact on our understanding of universal limits, the ultimate boundaries that define the behavior of the cosmos. These advances allow scientists to explore phenomena that were once purely theoretical, transforming abstract concepts into areas of exploration and experimentation. For instance, the development of powerful telescopes has revolutionized our capacity to observe distant galaxies, stars, and cosmic events. By capturing light that traveled billions of years to reach us, these instruments offer insights into the very early universe, giving clues about its expansion and the limits of space and time. Similarly, detectors placed in deep underground laboratories enable the observation of rare particles resulting from phenomena predicted by physics, such as dark matter interactions. This adds depth to our understanding of the foundational components of the universe, pushing the boundaries of what we deem knowable. In particle physics, advancements in collider technology have allowed researchers to smash particles at unprecedented speeds, recreating conditions just after the Big Bang. This helps to probe the fundamental forces in particles that govern the universe, revealing if and where our current models of physics hit a ceiling, whether due to energy limitations or unexplained behaviors. Moreover, improvements in computational technologies empower simulations that model complex physical interactions, visualizing scenarios that are too difficult or impossible to recreate in the lab. These simulations can test theories about black holes, the behavior of time and space, and the limits of known physics under extreme conditions. Every new technological development opens up pathways to challenge existing theories and explore areas we previously thought were off-limits, prompting a continuous reevaluation of what we know about the universe and its fundamental limits. Each breakthrough serves as a stepping stone, paving the way for deeper inquiries about the very nature of reality. Data analysis from space missions plays a crucial role in deepening our understanding of the universe. When a spacecraft is launched, it collects vast amounts of information about various celestial bodies, cosmic phenomena, and the conditions of space itself. This data can include readings on temperature, light composition, and even the gravitational effects of objects in space. Through meticulous analysis of this information, scientists are able to draw meaningful insights. For example, observations from missions studying distant planets can reveal their atmospheric conditions, helping us to ascertain whether certain planets might support life. Additionally, data gathered from telescopes observing light from ancient stars provides clues about the formation and evolution of the universe itself. Moreover, Space missions often investigate fundamental questions, such as the origin of cosmic rays, the presence of dark matter and dark energy, and the behavior of black holes. By analyzing these data sets, researchers can create models and simulations, allowing them to predict how celestial phenomena might behave. This understanding can lead to breakthroughs in physics and astronomy, guiding future explorations and informing our knowledge of fundamental forces. The collaborative effort involved in data analysis also promotes the sharing of knowledge across the scientific community. As different missions might focus on diverse aspects, their combined data enriches our understanding and helps to verify or challenge existing theories. Ultimately, the role of data analysis from space missions goes beyond mere observation. It serves as a powerful tool that transforms raw information into profound discoveries about the cosmos and our place within it. Computer simulations serve as powerful tools that help us visualize and understand the vast and often abstract areas of the universe's outer regions. Think of these simulations as intricate models that mimic real-world physical processes on a smaller, manageable scale. By creating algorithms that replicate the fundamental laws of physics, scientists can explore complex phenomena that would be difficult or impossible to observe directly. In outer space, conditions can vary dramatically, from the dense formations of stars to the elusive patterns of dark matter that are believed to exist in large amounts but cannot be seen directly. Through simulations, researchers can create virtual environments that allow them to experiment with different variables and scenarios. For example, they can adjust the mass of celestial bodies or the rates of expansion of different regions of space to see how these changes affect gravitational interactions and the overall structure of the universe. Moreover, simulations can help illustrate phenomena like galaxy formation and the cosmic web, a structure that resembles a giant tangled network filled with nodes of galaxies. By visualizing the evolution of such structures over billions of years, scientists gain insight into how galaxies evolve, interact, and cluster together. These simulations also provide a testing ground for theories. If predictions made by a simulation align with observations from telescopes or other instruments, it strengthens our understanding of the universe's workings. Conversely, if they do not match, it prompts scientists to revisit and refine their theories. Ultimately, computer simulations make the abstract realm of the cosmos more tangible. They transform complex astrophysical concepts into engaging visuals that enhance our comprehension of the universe's grand design, revealing intricate relationships and patterns that define our outer space environment. Particle physics plays a crucial role in our understanding of the potential end of the universe, providing insights into the fundamental forces and particles that govern cosmic behavior. To grasp how these tiny building blocks can influence the fate of everything, we must first acknowledge that the universe consists of matter and energy, interacting through fundamental forces such as gravity, electromagnetism, and the strong and weak nuclear forces. One significant concept in particle physics is the Higgs boson, often referred to as the particle that gives mass to other particles. The properties of the Higgs field may affect the universe's overall stability. If stability was suddenly disrupted, it could lead to a catastrophic event, the so-called vacuum instability. This hypothetical scenario suggests that a shift in the Higgs field could generate a chain reaction of particle transformations, potentially obliterating the existing universe and replacing it with a different state of reality. Additionally, particle physics provides insight into dark matter and dark energy, the mysterious components believed to make up a large portion of the universe. Dark matter, which interacts with ordinary matter only through gravity, contributes to the structure of galaxies. Meanwhile, dark energy is thought to be responsible for the accelerating expansion of the universe. If the balance and interactions between these forces shift, they could lead to various fates, ranging from a slow cooling as the universe expands indefinitely to a potential big crunch, where gravitational forces could eventually draw everything back together. Theoretical scenarios like the heat death of the universe imply that as energy becomes more evenly distributed across space, stars will burn out, galaxies will drift apart, and all forms of life will cease to exist in an increasingly cold and empty cosmos. Each of these outcomes, whether related to vacuum instability, dark energy, or the eventual depletion of usable energy, stems from the underlying principles elucidated by particle physics. By studying the smallest particles, we gain valuable perspective on both the cosmos' evolution and its ultimate fate, revealing that the path toward the end is as complex as the universe itself. Interdisciplinary research plays a crucial role in enhancing our understanding of the expansive boundaries of the universe. By drawing insights from various fields, including physics, astronomy, mathematics, biology, and even philosophy, scientists can approach questions from multiple angles, unlocking new perspectives that a single discipline might overlook. Scientific debates play a crucial role in advancing our understanding of the universe's edge, a place teeming with mysteries and profound questions. These discussions often bring together researchers with diverse perspectives and expertise, challenging established ideas and encouraging fresh thinking. When scientists engage in debate, they question assumptions, design innovative experiments, and develop new theories. This interactive process resembles a collaborative puzzle-solving effort, where each participant contributes pieces of knowledge and insights, leading to a fuller understanding of complex phenomena. Debates also pave the way for innovation in technology and methods, enabling researchers to gather data previously thought unreachable. In the grand quest to understand the universe, the collaboration of astrophysics, cosmology, and advanced technology continues to push the boundaries of what we know. Before the existence of stars, planets, and even light itself, there was a concept that has mystified humanity: nothingness. What does it truly mean for something to come from nothing? Join us as we delve into what may have existed before time and space. The period before the Big Bang is a tantalizing enigma that has intrigued scientists and cosmologists alike. Many theories attempt to grapple with what preceded this monumental event. One of the most compelling ideas is the concept of cosmic inflation. This theory suggests that, in the very first moments after the Big Bang, the universe underwent an incredibly rapid expansion. Although this primarily addresses what happened right after the Big Bang, rather than before it, it hints at the conditions that could have led to our universe's inception. Another perspective posits the existence of a singularity. A singularity is a point in which gravitational forces compress matter to infinite density prior to the Big Bang. If our universe originated from such a singularity, then all physical laws as we know them break down, making it challenging to define what before meant in this context. This notion implies a history where time itself may not have existed in any recognizable form, departing from our conventional understanding. Some scientists and researchers advocate for the cyclic model of a universe, where the cosmos undergoes endless cycles of expansion and contraction. In each cycle, the universe expands from a hot, dense state, only to eventually collapse back into itself, leading to a new Big Bang. This model suggests not only a past before our current universe, but a potentially infinite series of universes preceding it, each with their own unique variations. Then there's the concept of the multiverse, which theorizes that our universe might just be one of countless others, each with different physical laws and constants. In this scenario, the Big Bang could be seen as a bubble popping into existence in a larger sea of universes. Each of these theories offers distinct insights into the mind-boggling question of what came before our universe, emphasizing the complexity and the frontier nature of cosmological science. Quantum fluctuation introduces a layer of complexity in our understanding of a universe's inception. At the heart of these fluctuations lie the principles of quantum mechanics, a field that describes behavior on the tiniest scales, such as atoms and subatomic particles. In this realm, uncertainty reigns. Particles and energy can appear and disappear seemingly out of nowhere, driven by the inherent unpredictability of quantum states. This phenomenon suggests that the fabric of reality is far more dynamic than we might have previously thought. When scientists consider the origin of the universe, a notable hypothesis is the Big Bang theory, which posits that the universe began as an incredibly hot and dense state. Yet, if we apply the principles of quantum mechanics to this moment of creation, we are left grappling with the idea that during the first instance following the Big Bang, minute fluctuations in energy could have led to the uneven distribution of matter and energy we observe today in the cosmos. Instead of a singular, smooth beginning, these fluctuations hint at a chaotic, bubbling realm of possibilities, where tiny random variation could have been amplified over time to shape galaxies and cosmic structures. These quantum variations also raise intriguing questions about the very nature of creation itself. If the universe could emerge from a vacuum, with energy sparking into existence from nothingness, what does that say about existence? This challenges traditional views that see a clear boundary between nothing and something. It proposes that nothing is not actually an empty void, but a vibrant field teeming with potential, where fluctuations can lead to profound outcomes. Moreover, the implications of quantum fluctuations extend beyond our past into our understanding of the universe's fate. The ongoing dynamics of these fluctuations, as postulated by theories like cosmic inflation, imply that even now the universe is influenced by these subtle energy changes. The universe could still be unfurling in ways we barely comprehend, continuously shaped by quantum events. This interplay between the tiniest movements and the grandest structures in the universe tantalizingly underscores the interconnectedness of existence. The multiverse theory suggests that our universe is just one of potentially countless others, each with its own distinct characteristics and physical laws. This concept opens intriguing avenues for exploring conditions that may have existed before the Big Bang. If multiple universes exist, it raises a possibility that some of these universes could provide clues about the nature of reality prior to our universe's beginning. One of the fascinating implications of the multiverse theory is that it allows for various scenarios concerning the origins of universes. Some models propose that universes can emerge from a collision of other universes. This idea leads to the suggestion that our universe might not have simply burst into existence, but could have been born from interactions in a vast cosmic landscape. By studying these interactions, scientists might glean insights into the state of the universe before its inception, including parameters that governed it. Additionally, the multiverse offers a framework for considering different laws of physics that could have prevailed before the Big Bang. Each universe in the multiverse might have varied constants and forces, which would in turn influence the conditions leading up to their respective Big Bang events. Understanding these different sets of physical laws allows researchers to hypothesize about how the Big Bang occurred in our universe, as well as how other universes may have experienced their own distinct beginnings. On a more speculative note, the conditions before the Big Bang might be hidden within quantum fluctuations in a multiverse context. If our universe originated from a quantum state, exploring the dynamics of these fluctuations across several universes could uncover what precedes a familiar cosmic expansion. As researchers continue to unravel the intricacies of the multiverse theory, we may ultimately gain deeper insights into one of the most profound mysteries of cosmology, what existed before the universe we call home came into being. Cyclical universe models suggest that the universe undergoes an eternal series of expansions and contractions, effectively recycling itself through time. The central idea here is that, after reaching a maximum size, the universe begins to collapse under its own gravity, eventually leading to what is known as the Big Crunch. This collapse is thought to compress all matter and energy back to an incredibly hot and dense state, similar to the conditions that might have existed just before the Big Bang. One of the most prominent versions of this theory is the oscillating universe model. In this framework, the universe experiences a continuous cycle of expansion, contraction, and rebirth. Each expansion phase, often referred to as a Big Bang, would create a new universe shaped by the remnants of the previous cycle. This continuous loop proposes that the universe is not just a one-time event, but rather a lasting entity that transforms and evolves over infinite time. In some variations of cyclical models, like the one proposed by string theory, the universe could also experience cosmic bouncing, where the universe avoids singularities entirely. Instead of collapsing into a point of infinite density, the universe's expansion would slow down, halt, and then reverse into a contraction phase, initiating a bounce back into an expansion phase. This model accommodates the current understanding of cosmic expansion while incorporating gravitational and quantum effects. These principles challenge a conventional notion of a linear universe that began singularly and will end in a freezing fate or Big Rip. Instead, they explore fascinating possibilities of cosmic longevity, suggesting that not only does a universe change over time, but it also persists through an endless cycle of destruction and renewal, eternally crafting new realities from the ashes of the old. Cosmic inflation is a fascinating idea that describes the very early moments of our universe's existence. Imagine a period just after the Big Bang when the universe expanded at an astonishing rate, exponentially stretching in size. This rapid expansion, which occurred within a fraction of a second, helped smooth out any irregularities and set the stage for the cosmos as we know it today. It provides a framework for understanding how the universe reached its large and uniform state as it grew from a hot, dense point to a vast, cooler expanse. Now, when we consider the universe before this expansion, things become intriguing. Traditional models of the Big Bang suggest that time and space, as we know them, originated from that singular event. However, cosmic inflation opens up possibilities about conditions and structures that might have existed prior to our universe's explosive birth. Some theories suggest that our universe could have emerged from a prior cosmic state, or even from fluctuations in a quantum vacuum, a field that exists even in the absence of matter. In these theoretical landscapes, the universe isn't necessarily the first of its kind. It may be one of many oscillating universes, or part of a multiverse where different regions exist with varying physical laws. These ideas challenge our understanding of time, because without a clear beginning, we ask ourselves what before even means in this context. It evokes a sense of wonder about what the universe was like, and raises profound questions about the nature of existence itself. As researchers delve deeper into cosmic inflation, they explore its implications for understanding reality itself. It suggests a universe that is not static, but dynamic and ever-changing, shaped by complex processes that may stretch far beyond our current perception of time and space. This interplay between cosmic inflation and the theories of existence before our universe continues to inspire questions and excite imagination across the fields of cosmology and physics. Singularities are extraordinary points in the fabric of space and time where the usual laws of physics break down. They are typically associated with very dense objects. In the context of the universe's beginning, the most famous singularity is the one believed to have existed at the moment of the Big Bang. Here, all matter and energy were concentrated into an infinitely small point, resulting in extreme temperatures and densities. This singular state birthed the entire universe as we understand it, marking the inception of time and space approximately 13.8 billion years ago. As we delve deeper into the nature of singularities, they also appear in the center of black holes. These enigmatic regions create immense gravitational pulls so strong that not even light can escape. When stars reach the end of their life cycles and collapse under their own gravity, they form black holes where singularities reside. While the implications of singularities this way reveal aspects of our universe's life cycle, they also raise questions about the ultimate fate of matter, energy, and even information itself. Thinking about precursors to the universe, singularities invite us to consider theories like cosmic inflation. This concept proposes that, shortly after the Big Bang, the universe underwent an exponential expansion. Some researchers suggest that the dynamics of singularities could play a role in understanding what might have preceded the Big Bang itself, or how the universe evolves past the singularities within black holes. Thus, singularities serve not only as a cornerstone in understanding the universe's origins, but also as a window into complex processes that shape its evolution. They challenge our perspectives, pushing the boundaries of what we know, and inviting us to ponder the mysteries that lie beyond our current scientific grasp. String theory presents a fascinating framework that seeks to unravel the mysteries of the universe, particularly the enigma of what existed before the Big Bang, the moment that marked the beginning of everything we know. At its core, string theory suggests that the fundamental building blocks of the universe are not point-like particles, as traditionally thought, but rather tiny vibrating strings. These strings exist in multiple dimensions beyond the familiar 3 dimensions of space and one at a time. This opens up a new way of thinking about the cosmos and its origins. By proposing additional dimensions beyond our common experience, string theory provides a potential explanation for conditions that may have existed prior to the Big Bang. It suggests that these extra dimensions could represent various states of energy and existence, where the universe was in a highly dense and chaotic state. In this pre-Big Bang scenario, the string could interact in ways we are still striving to comprehend, potentially giving rise to the explosive event that initiated our observable universe. Through this lens, string theory does not seek to locate a definitive before, but instead offers a framework for reconstructing the universe's earliest moments. Moreover, in seeking to unify all fundamental forces in nature, string theory provides insights that are not merely theoretical, but can also influence how we approach questions about the universe's origin. For instance, phenomena related to black holes and the fabric of space-time could be better understood through the principles of string theory. By contemplating how gravity interacts with quantum mechanics, researchers hope to glimpse the conditions that could have set the stage for the Big Bang itself, potentially bridging our understanding of what might precede our universe. While string theory is still not universally accepted and remains a topic of debate among physicists, its implications encourage scientists to rethink foundational concepts of time, space, and existence. What came before is no longer a simple void, but a vibrant tapestry of possibilities, governed by the laws of string dynamics, inviting relentless curiosity and exploration into the very nature of reality itself. What came before is no longer a simple void, but a vibrant tapestry of possibilities, governed by the laws of string dynamics, inviting relentless curiosity and exploration into the very nature of reality itself. This investigation holds the potential to revolutionize our understanding of a universe's origins, offering tantalizing glimpses into the tapestry woven by the strings of existence. Dark matter and dark energy play pivotal roles in our understanding of a universe's origins and its ongoing evolution. Despite being unseen, they significantly influence the structure and behavior of the cosmos. Dark matter, which is estimated to constitute approximately 27% of the universe, serves as a gravitational framework, ensuring that galaxies, clusters of galaxies, and even larger structures remain intact. Its existence is inferred from the gravitational effects on visible matter rather than being directly observable. Without dark matter, galaxies would not have a necessary gravitational pull to hold together their stars and other components, leading to an entirely different cosmic landscape. On the other hand, dark energy, which makes up about 73% of the universe, has been a source of curiosity and intrigue among astronomers. This mysterious force is believed to be responsible for the accelerated expansion of the universe, a phenomenon first noted in the late 20th century, when distant supernovae were observed to be moving away from us at an increasing velocity. The nature of dark energy is still largely unknown, and it challenges our traditional understanding of gravity and the fabric of space-time itself. The combination of dark matter and dark energy changes the course of cosmic history. After the Big Bang, dark matter helped to clump together matter, leading to the formation of the first stars and galaxies. Meanwhile, as the universe expanded, dark energy emerged, overpowering the gravitational attraction of matter and driving galaxies further apart. This interplay suggests a dynamic cosmos, where invisible opponents greatly influence visible phenomena. Delving into these concepts invites fundamental questions about the universe itself. What are the true identities of dark matter and dark energy? Are they merely product of the equations of physics, or do they represent a deeper layer of reality yet to be discovered? As research continues, scientists hope to unravel the mysteries that dark matter and dark energy present, bringing us closer to a comprehensive understanding of the cosmos and our origins within it. The idea of a baby universe is a fascinating concept within the framework of cosmology, arising from our efforts to understand the origins and development of the universe. This notion suggests that, much like the universe we inhabit, smaller self-contained universes can emerge from a parent universe, each exhibiting its own set of physical laws and constants. This theory aligns with certain interpretations of cosmic inflation, wherein the rapid expansion of space shortly after the Big Bang could give rise to pocket universes or baby universes. Current cosmological theories propose that, during the early moments after the Big Bang, fluctuations in energy could cause regions of space to inflate dramatically. Some of these regions might continue expanding and evolve into distinct universes, each potentially disconnected from one another, yet emerging from a shared cosmic origin. This scenario raises intriguing questions about the nature of reality, existence, and whether there might be an infinite number of these baby universes, forming a multiverse beyond the limits of our observable universe. One of the most enthralling aspects of the baby universe concept is the implications it carries for quantum mechanics. In quantum theory, particularly in Stephen Hawking's discussions about black holes, the idea emerges that black holes might not only capture matter but could also facilitate the birth of new universes. According to this perspective, the singularity at the center of a black hole could act as a gateway, where the conditions are ripe for a fresh universe to emerge, potentially replete with its own specific laws of physics. As researchers delve deeper into these theories, they continue to explore how these baby universes might connect with a broader structure of reality. Questions about the fate of these universes, their potential for interaction with our own, and the fundamental laws that govern them captivate scientists and philosophers alike. The more we learn, the more we realize how much remains to be discovered about the cosmos, and the concept of baby universes offers a remarkable glimpse into the possibly boundless nature of creation itself. When we refer to nothing, we are diving into one of philosophy's most profound and intriguing concepts. Nothingness implies the absence of anything that can be perceived, measured, or even imagined. It stands in stark contrast to existence, which is marked by entities and phenomena, everything that fills a universe. This dichotomy raises deep questions about the nature of reality itself and our understanding of existence. The idea of nothingness challenges us to think about the very fabric of existence and prompts us to ask what it means to be. For instance, in quantum mechanics, there is a fascinating suggestion that even what we perceive as empty space is teeming with potential. Particles may not be permanently visible but can arise, queue, and disappear from this so-called nothingness. This leads to the conclusion that, even in the absence of matter and energy, the potential for creation lurks just beneath the surface, giving us a glimpse into a universe filled with possibilities. Philosophically, the concept of nothing invites reflection on existence's value and significance. If we were to grasp the fullness of nothing, it could instill a greater appreciation for everything that surrounds us, the stars, the planets, and even the air we breathe. Life becomes a remarkable phenomenon against the backdrop of emptiness. Each tiny particle in our bodies, every blade of grass, and all the expansive cosmos stand as testaments to existence where there could have been none. Our explorations into nothingness ultimately push the boundaries of what we know. They stir curiosity and wonder, inviting us to consider the very nature of reality. If nothingness can exist and can transition into something, it poses fundamental questions about creation, the universe's origins, and our place within it. In grappling with these ideas, we begin to understand that existence is not merely about being present, but also about appreciating the intricate dance between existence and potential what could be even in the vast realms of nothingness. Philosophers have grappled with the notion of nothingness for centuries, pondering its implication for existence, reality, and meaning. In ancient Greece, thinkers like Parmenides argued that nothingness could not truly exist, because to speak of nothing is to imply a lack of being. For Parmenides, existence itself was the only certainty, and any idea of nothingness was inherently contradictory. This philosophical inquiry laid the groundwork for later explorations of existence versus non-existence. As philosophy progressed through the ages, figures like René Descartes brought a new perspective with his famous assertion, "I think, therefore I am." Descartes suggested that the act of doubt or thought proved the existence of the self, distinguishing existence as a fundamental quality. This assertion further highlighted the tension between being and nothingness, that one must acknowledge existence to even contemplate the void. The challenge remained: how does one conceptualize what it means to exist in a universe that could also embody the absence of all things? The existentialist movement in the 20th century brought nothingness to the forefront, particularly with philosophers such as Jean-Paul Sartre. Sartre posited that nothingness plays a critical role in shaping human existence. He argued that individuals face the daunting freedom of choice, creating meaning in an otherwise indifferent universe. By recognizing that life lacks inherent purpose, one must confront the emptiness that surrounds existence and ultimately take responsibility for their choices. This dialogue between nothingness and existence continues to resonate in contemporary thought. Throughout history, the exploration of nothingness has stirred deep philosophical discussions about what it means to exist. From Parmenides to Sartre, each philosopher contributed unique insights, shaping our understanding of the profound complexities that arise when we consider both being and the absence of being. This enduring interest in nothingness reveals not only the limits of human understanding, but also the relentless quest to find meaning amidst the void. The debate over nothing significantly complicates our discussions about the universe's origins, particularly in the realm of cosmology and philosophy. Nothing is a concept that elicits more confusion than clarity, especially when we consider that in physics, even the emptiest regions of space still contain quantum fluctuations. These fluctuations suggest that nothing is not truly devoid of activity or potential, challenging our traditional notions of emptiness. Many scientists and philosophers argue about the nature of nothingness. If we consider that nothing could give rise to something like the universe, we must grapple with the potential mechanisms involved. Theories such as quantum mechanics propose that particles can emerge spontaneously from a vacuum, which adds a fascinating layer to the question of how the universe began. This suggests that the very act of creation could be a natural occurrence within a realm we might not yet fully understand, blurring the boundaries between existence and non-existence. Further complicating discussions are the philosophical implications tied to nothing. Different philosophical traditions present various interpretations of existence, and these perspectives can influence scientific inquiry. For example, if nothing is a state of being without properties, what does that imply about our understanding of time, space, and causality? These philosophical angles force scientists to consider not only empirical evidence but also foundational assumptions regarding existence and reality itself. As we delve deeper into these questions, the interplay between science and philosophy becomes evident. The debates surrounding nothing push us to reconsider our models of the universe's origins, leading to more profound inquiries that inspire both scientific innovation and existential reflection. In this way, nothing becomes a paradoxical catalyst that fuels exploration into the very essence of our universe. Existentialism delves into the nature of existence and the individual's experience in a seemingly indifferent universe. In cosmological debates, the concept of nothingness can be particularly perplexing, as it challenges our understanding of being and reality. Philosophers such as Jean-Paul Sartre and Martin Heidegger explored how the recognition of nothingness can lead to profound existential crisis. They asserted that the awareness of nothingness strips away illusions, leaving individuals to confront their existence in a universe that may appear devoid of inherent meaning. This philosophical framework encourages us to ponder our significance within the cosmos. When we consider the vastness of space and the possibility of cosmic emptiness, existentialism helps articulate that nothingness is not simply an absence, but also a crucial aspect of understanding existence itself. The void can represent potential, an openness where new ideas and realities might emerge. It prompts us to question what it means to exist, urging us to find or create meaning rather than accept a predetermined cosmic order. In cosmology, these existential questions lead to rich discussions about the origins of the universe and our place within it. Theories surrounding the Big Bang often brush against the concept of nothingness, as they explore what existed before this initial expansion, and whether it was indeed a void or something yet to be defined. By engaging with these profound inquiries, existentialism invites scientists and philosophers alike to explore the idea that our search for meaning can flourish even in the face of cosmic silence. Ultimately, the existentialist perspective serves as a bridge between philosophical contemplation and scientific inquiry, encouraging a dialogue about how we grapple with the implications of nothingness in the grand tapestry of the universe. Through this lens, nothingness transforms from a mere absence into an invitation for exploration as we navigate our journey through existence and the mysteries that lie beyond. The concept of everything emerging from nothing invites a cascade of philosophical questions that delve deep into the nature of existence itself. For centuries, thinkers have grappled with what it truly means for something to come from nothing. If the universe, with its galaxies, stars, and intricate life forms, sprang into being from a state devoid of matter or energy, one might ponder the very essence of creation. What does that imply about causality and the beginning of time? How can something emerge if there was once nothing? This notion also prompts us to question the nature of nothingness itself. Is it merely a vacuum, an absence, or does it possess properties of its own? The philosopher Martin Heidegger famously mused on the idea of being in nothingness, suggesting that understanding existence requires us to grapple with non-existence. Such reflections challenge us to explore whether nothing can truly be considered a state, or if it is merely defined in relation to something. This leads us to contemplate the limits of human understanding and language. How can we describe absence using terms rooted in presence? Then what does that mean for meaning in our lives? Is meaning something we impose onto the universe, or does it arise inherently from the interactions within it? Questions about the randomness of existence versus a predetermined order provoke reflections on whether there is a guiding force or intention behind this remarkable unfolding of reality. Ultimately, these inquiries do not just reside in abstract thought, they resonate with our experiences and beliefs. They invite us to consider our own place within this vast cosmos and encourage a deeper examination of the very fabric of reality. Exploring the emergence of everything from nothing illuminates our understanding of existence, challenging us to reflect on the most profound questions of life, purpose, and the universe we inhabit. Eastern philosophies, particularly those emerging from traditions like Hinduism and Buddhism, often embrace a concept of pre-existence that aligns with ideas of cycles, reincarnation, and unity with the cosmos. Within Hindu thought, the belief in the soul or Atman suggests that each individual has existed in various forms throughout countless lifetimes. This journey is deeply intertwined with the concepts of karma and dharma, where one's actions in past lives shape current and future experiences. Life is seen as continuum, an expansive cycle of birth, death, and rebirth, pushing individuals towards the ultimate goal of liberation known as moksha, a state of oneness with the divine. In contrast, Western philosophies, particularly those rooted in Judaism, Christianity, and Greco-Roman thought, typically attach a more linear understanding of existence. Pre-existence is often viewed through the lens of a singular life meant to prepare individuals for an eternal afterlife. For instance, in Christian theology, the soul is believed to be created uniquely by God at the moment of conception, with one's earthly life serving as a test for eternal destiny. Personal identity in this lens is tied closely to actions within a single lifetime, emphasizing notions of salvation and moral judgment rather than cycles of existence. When exploring these ideas, fascinating variations emerge within each tradition. For Buddhists, the focus lies not only on the collective past lives, but also on the desire to transcend suffering through enlightenment and eventual liberation from the cycle of rebirth. This focus on psychic transformation underscores a shared interconnectedness of all beings, prompting individuals to cultivate compassion and mindfulness in the present. Both philosophical traditions ultimately seek to offer insights into the nature of existence and the human experience, yet they arrive at remarkably different interpretations of pre-existence. The exploration of these concepts can lead to rich discussions about the essence of identity, purpose, and the interconnectedness of all life, revealing a diverse tapestry of human thought that continues to captivate minds seeking to understand their place in the universe. The notion of something from nothing presents a fascinating challenge to long-held beliefs about causality. Traditionally, we understand that every effect must have a cause. This principle is deeply embedded in our understanding of the universe, where events lead into one another in a chain of cause and effect. However, the concept of creating something from nothing disrupts this neat distinction, leading us to question the very foundations of how we perceive existence. Take, for instance, modern theories in cosmology that suggest the universe itself may have emerged from a state of nothingness. In this context, nothing doesn't imply an empty void, but rather a quantum vacuum filled with energy fluctuations where particles could spontaneously rise. This idea of spontaneous generation defies conventional logic. If existence can emerge without a pre-existing cause, then the linear narrative of cause and effect becomes more complex and nuanced. Philosophers and scientists grapple with this phenomenon, as it implies that the universe might not adhere strictly to our intuitive understanding of causality. Such insights stimulate rich discussions about the nature of reality, urging us to broaden our conceptual frameworks. Additionally, they raise profound questions about the origins of everything, from particles to galaxies, and even the laws of physics themselves. As we delve into these inquiries, we find ourselves at the intersection of philosophy, physics, and metaphysics. The paradox of something from nothing not only challenges our views of causation, but also invites a deeper exploration of existence, leading to a richer understanding of the cosmos and our place within it. The philosophical concept of the void can play a significant role in deepening our understanding of the early universe. In cosmology, scientists often refer to the void as the absence of matter, an empty space where nothingness seems to prevail. This notion aligns intriguingly with the early conditions of our universe, which, according to theories, was once a vast expanse of nearly uniform energy and radiation before the emergence of matter and structure. At the very beginning, shortly after the Big Bang, the universe was in an incredibly dense and hot state where fundamental particles barely existed. As it expanded, the void grew more pronounced. Understanding this void helps scientists explore the properties of dark energy and matter. In fact, the void is essential for the formation of cosmic structures like galaxies, as they emerge from the gravitational clumping of matter within an otherwise empty space. This layering of density across the cosmos illustrates how the void is not just absence, but also a crucial component in cosmic evolution. Moreover, the philosophical implications of the void prompt deeper questions about existence and reality itself. In contemplating the void, we reflect on the transition from nothingness to abundance that marks our universe's history. The tension between nothingness and substance invites discussions about the nature of creation, the laws governing the universe, and the boundaries of our scientific knowledge. These explorations enrich our scientific perspective by merging abstract thinking with empirical evidence. In exploring such philosophical dimensions, we can appreciate that the universe's intricate design is shaped not only by what exists, but also by what does not exist. This multidimensional approach fosters a more profound comprehension of the early universe, merging scientific inquiry with philosophical reflection, ultimately enriching our quest to understand where we came from and how the cosmos came to be. Human concepts of creation and destruction play a significant role in how we interpret the origins of the cosmos. Throughout history, civilizations have crafted narratives about the universe's beginnings that often reflect their own experiences with creation and the cyclical nature of life. In many cultures, the act of creation is deeply intertwined with mythology and spirituality, serving as a way to understand the vast mystery surrounding us. These narratives embody the hope of new beginnings, often symbolized by the birth of stars or the emergence of whole galaxies from cosmic dust. On the flip side, the concept of destruction adds another layer to our understanding of cosmic events. Destruction is not simply an end, it is frequently seen as a precursor to new creation. For instance, the death of a massive star culminates in a spectacular explosion known as a supernova, which disperses elements into space, eventually contributing to the formation of new stars and planets. This interplay between creation and destruction provides insight into the universe's cyclical processes, where endings pave the way for beginnings. As we study cosmic beginnings through the lens of science, such as the Big Bang Theory, these human concepts shape how we relate to the enormity of the cosmos. The Big Bang, often referred to as the moment our universe began, resonates with human notions of birth and creation, while the eventual fate of the universe, whether it ends in collapse or expansion, sparks reflections on destruction and renewal. By examining these themes, we can appreciate both the scientific and philosophical dimensions of the cosmos, leading to a richer understanding of not just where we come from, but also what it means to exist. Ultimately, our interpretations of the universe are colored by these fundamental human experiences. They help us frame questions about existence, purpose, and the intricate dance between creation and destruction that is inherent in nature. As we look at the stars and contemplate our origins, these themes remind us that our place in the universe is not merely an observation, but a profound connection to the very fabric of what's possible in the grand scheme of cosmic history. The early universe was a place of extremes, characterized by conditions vastly different from anything we experience today. During the Planck era, which lasted from 0 to approximately 10 to the minus 43 seconds after the Big Bang, the universe was incredibly small, incredibly hot, and unimaginably dense. At this time, all the physical forces we know, gravity, electromagnetism, the strong force, and the weak force, were unified into a single force, meaning that the laws of physics as we understand them were not yet distinguishable from one another. The temperatures were so overwhelming, estimated to be around 10 to the 27 degrees Celsius, that the very fabric of space and time began to behave in ways that challenge our understanding of physics. At these energy levels, fundamental particles like quarks and electrons were in a state of constant flux. Matter as we recognize it had not yet formed. Instead, the universe was filled with a hot, dense soup of energy and radiation, where particles were continually being created and annihilated. This chaotic environment is thought to have set the stage for the eventual separation of forces as the universe cooled, allowing particles to take on distinct identities and the first building blocks of matter to emerge. As the universe expanded and cooled further, it transitioned out of the Planck era into the next phase, known as the Grand Unification era. However, the distinctive characteristics of the Planck era continue to intrigue scientists today. The laws governing this epoch are believed to have profound implications for our overall understanding of the universe, including insights into the origins of space and time. One of the outstanding questions is whether the theory of quantum gravity can successfully describe this early moment, an endeavor that could unlock the secrets of the universe's birth and provide a more comprehensive understanding of its evolution. Ultimately, the conditions during the Planck era were foundational, paving the way for everything that followed. The mysteries wrapped up in this seemingly brief moment remind us just how much more there is to discover about our universe's earliest days, teasing the boundaries of modern physics and our comprehension of reality itself. During the Planck epoch, which occurred within the first 10 to the negative 43 seconds after the Big Bang, the very fabric of time and space operated under rules that are unfathomable to our everyday experience. At this minuscule moment, all the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces were unified. The energies involved were so extraordinarily high that quantum effects dominated, and space-time itself was likely turbulent and chaotic. unlike the smooth, predictable nature we observe today in our current understanding. Time flows steadily, and space is described by the dimensions we can perceive. However, at the Planck scale, the granularity of space-time becomes significant. We can envision time not as a continuous river, but more like a series of discrete moments or events that are interspersed with quantum fluctuations. This means that the conventional beginnings and ends of events may lose their clear definitions, challenging our notions of causality and sequence. Moreover, distances in space-time itself seem to be on a scale that our senses and current physics cannot readily grasp. The dimensions we take for granted were either non-existent or entirely different, as space-time may have been so compact that it was hard to distinguish between the effects we now identify as time and space. Theoretical physicists suggest that what we understand as the fabric of the universe was fluid and pliable, continuously influenced by quantum uncertainties. Thus, comprehending the universe during the Planck epoch requires grasping a reality where physics diverges sharply from the laws governing our macroscopic world. As the universe expanded and cooled, these unified forces began to separate, and space-time settled into the more structured framework we are now familiar with. This transformation set the stage for the rich tapestry of cosmic events that followed, leading ultimately to the universe we inhabit today. High-energy physics plays a pivotal role in exploring the mysteries of the universe, particularly when it comes to understanding the moments leading up to the Big Bang. This branch of physics investigates the fundamental particles and the forces that govern their interactions at energies far beyond what we experience in our everyday lives. By examining these high-energy scenarios, scientists can recreate conditions similar to those thought to exist in the early universe, providing valuable insights into its origins. When we consider the moments prior to the Big Bang, we venture into territory where current physical theories become particularly vital. Models such as quantum field theory allow physicists to probe the behaviors of fundamental particles when energy densities were extraordinarily high. This exploration can reveal how the fundamental forces, like gravity and electromagnetism, may have operated in concert during that chaotic period. Specifically, high-energy collisions in particle accelerators such as the Large Hadron Collider simulate the extreme conditions of the early universe and can help us uncover clues about particle interactions that might have taken place at that time. Furthermore, high-energy physics delves into phenomena like the inflationary model, which posits a rapid expansion of space just after the Big Bang. This model suggests that quantum fluctuations in the energy field could have seeded the large-scale structures we observe in the universe today. By studying these fluctuations and the properties of particles at high energies, researchers aim to paint a clearer picture of how the universe evolved from its initial singularity. As scientists continue to push the boundaries of high-energy physics, each new discovery adds a layer to our understanding of cosmic history. While many questions about the events before the Big Bang linger, the insights gained from high-energy physics bring us closer to unraveling the intricate tapestry of the universe's beginnings. Scientists have developed several inventive methods to study the conditions of the early universe, all while navigating the challenges posed by limited observational evidence. One of the primary tools in this quest is the field of cosmology, which combines theoretical models with available data to reconstruct the universe's infancy. By analyzing the cosmic microwave background radiation, the afterglow of the Big Bang, researchers can glean vital clues about the universe just a few 100,000 years after its birth. This faint radiation is remarkably uniform, but it contains tiny fluctuations that reflect variations in density, providing insights into how matter was distributed throughout the developing cosmos. In addition to analyzing cosmic microwave background radiation, scientists utilize simulations and models based on the laws of physics to understand early universe conditions. These models rely on principles of general relativity and particle physics to replicate the environment just moments after the Big Bang. By adjusting various parameters in their simulations, researchers can see how different conditions could lead to the formation of elementary particles, atoms, and eventually stars and galaxies. This modeling is essential because it allows scientists to explore scenarios that lie beyond the realm of direct observation, helping to build a cohesive narrative of cosmic evolution. Moreover, scientists investigate the distribution of large-scale structures like galaxies and clusters of galaxies in the present universe. Observing how these structures formed and evolved gives clues about the initial conditions that guided their growth. For instance, the distribution of dark matter affects how galaxies cluster together over time, leading researchers to infer characteristics of the early universe based on current large-scale structures. Researchers are also turning to gravitational waves, ripples in space-time caused by massive events like black hole mergers. Detecting these waves opens a new window into high-energy processes that could have occurred in the very early universe, adding another layer of understanding to conditions that shaped our cosmic history. By synthesizing direct observations, theoretical models, and emerging technologies, scientists continue their quest to unravel the mysteries of the early universe, revealing the profound and intricate story of our existence among the stars. The density and temperature of the universe during its infancy were pivotal in determining its evolution. A mere fraction of a second after the Big Bang, the universe was an incredibly hot and dense environment. Temperatures soared to trillions of degrees, causing matter and energy to coexist in a unique state known as a quark-gluon plasma. In this state, the fundamental particles, quarks and gluons, roamed freely without being confined within protons and neutrons, marking a time when the fabric of the universe was still being woven. As the universe expanded, it cooled significantly. This cooling allowed the quarks to combine and form protons and neutrons. Approximately 3 minutes post-bang, the density of the universe enabled these particles to undergo processes that led to the creation of light elements such as hydrogen and helium. This era is known as Big Bang nucleosynthesis. The proportions of hydrogen and helium formed during this epoch would go on to play a crucial role in the development of stars and galaxies. The interplay of density and temperature set the stage for the universe's large-scale structures. Conditions that prevailed allowed gravity to start clumping matter together, leading to the formation of stars and galaxies over the billions of years that followed. A higher density meant that regions of space could attract more matter, becoming denser and eventually collapsing to form celestial bodies. Conversely, regions of lower density would expand and cool down, resulting in voids between galaxies. Understanding the early universe's density and temperature helps scientists decipher cosmic microwave background radiation, the afterglow of the Big Bang. This faint radiation, observed today, carries the imprint of the universe's state when it transitioned from a hot, dense environment to the colder cosmos we see now. By studying these remnants, we gain insight into the conditions that shaped our universe, enriching our understanding of cosmic history. Quantum mechanics offers a remarkable lens through which to explore the nature of reality, especially when considering the conditions that may have existed before the creation of the universe. At the quantum level, the universe is fundamentally different from our everyday experiences. Instead of fixed states, particles exist in probabilities, capable of being in multiple states simultaneously until measured. This phenomenon prompts us to think about existence itself. If particles can fluctuate and take on various forms, could the fabric of reality before the universe's birth have been a vast sea of probabilities rather than a concrete state? This idea aligns with the concept of quantum fluctuations. In simple terms, quantum fluctuations suggest that even in the emptiest regions of space, energy can spontaneously appear and vanish, leading to variations in energy levels. Such fluctuations might have contributed to the birth of the universe, potentially giving rise to the Big Bang itself. Before that grand event, one might speculate that the universe did not exist in a traditional sense. Instead, it may have been a latent potential, an unmanifested collection of quantum states yearning to coalesce. Furthermore, theories such as a multiverse contemplate that our universe is merely one of countless others existing simultaneously. In these scenarios, a quantum realm pre-exists our universe, where different physical laws or constants could generate numerous realities. Each variation branches off in an infinitely vast and diverse cosmos, challenging our classical understanding of existence. If our universe sprang from such a realm, the implications for understanding time, space, and reality itself become monumental. Tapping into quantum mechanics might allow us to navigate the mysterious terrain of what lay before creation. It raises profound questions. What does it mean to exist? And how do probabilities shape our experiences? By expanding our understanding through the prism of quantum theory, we inch closer to deciphering the enigma of reality itself and perhaps the very origins of everything we know.